So I give a short introduction to
Okay, yeah.
Akash.
Hi, everyone. I'm Akash. I will be presenting our Tiny Action Challenge. So first, this is a low resolution action cognition. It's going for the second year. So this challenge is organized by UCF CRCV group. The challenge is led by Professor Rawat and Professor Shah. And there are multiple PhD students from the lab and the postdoc Shruti Vyas. So the agenda for today's talk would be, first I will introduce the challenge, and then we will go through the each top 3 performers for the challenge. So the first is why we should look into tiny actions. So tiny actions, they are more common in real world. They have come from some surveillance, security, and autonomous driving videos. Here we can see that the person is living from the car. There is interaction with the between humans and a human and a vehicle. However, if you look, compare it with the existing data sets such as EVA, so over here, the focus is totally on the person, and it covers the majority of the focus on the actor. And so it's helpful maybe in the for the robotics application, but if you come look into the surveillance and security purposes, it's not at all helpful. That's why we need tiny action datasets and all challenge. So in activity recognition, there has been existing research, but we have been using high quality videos. We have existing data sets such as UCF 101, GHMDB, and kinetics. These are some examples from each of the data sets, and we can see that the actor here covers a major portion of the frame and is like the center of the attention. So initial efforts for the tiny action is from the action cognition in low resolution videos. So we synthetically, firstly, videos have been downsampled, and then, but they does not show an realistic low resolution video. So even if we see that if we downsample the video from each of these frames, the main content or information is still intact. However, we propose a tiny action data set which has a realistic low resolution. We extended it from Virat surveillance data set. So over here, we can see that a person leaving the structure on the background, there is interaction with the car and everything. If we look on the graph on the right side, so on the x-axis, we have different data sets. On the y-axis, we have average actor of the size for each data set. So if we look for the EVA and GHM data set, they are like 30% cover the whole frame. If you go to UCF 101, that's like 15%, and for the Virat, it's almost negligible to 0%. Now coming to the tiny Virat data set, it has realistic low resolution videos. It has natural tiny actions. We extract these videos from surveillance. So camera is placed at a distant place. Actions are tiny, and there are lack of details such as it is blurry or foggy. Now, tiny Virat data set, it's a multi-level data set. So we have multiple actions such as carrying, walking, or carrying, standing at the same time in the videos. And for each action, we have multiple resolutions as well. Going to the depth for varying resolutions, looking in this graph, on x-axis, we have different actions. And on the y-axis, we have the number of samples. We color coded how the resolution of the different resolution of the videos. So if the resolution is between 0x0 to 20x20, it's color coded as blue. If it is 20x20 to 40x40, it's color coded as orange, and so on. So if we look over here, we can see that walking and carrying and standing, they are pretty have a very small resolution. Walking has equal distribution for the blue as well as the orange color coded. So there has been a lot of variations in the resolution for each of the actions. Now comparing the tiny Virat with existing data set. So firstly, we look into the second column. So the resolution of UCF and HMDB is fixed at 320x240. Whereas for tiny Virat, it varies from 10x10 to 128x128. That makes this dataset more challenging. The average number of frames is 93 for tiny Virat. Then it's a multi-level dataset compared to UCF and HMDB, which is not a multi-level dataset. The number of classes is 26, and the number of videos is roughly around 13,000. Now for this challenge, we extend it to all the other parameters are same, except the number of videos, which we extended double it this time to 26,000. This year, we also extended from recognition task to detection task. So for spatiotemporal action detection, we need to do detection per frame. So there has been existing data sets such as UCF 1124. The issues in that is like it's only single action class and it's centered on the actor. That does not depict the real world scenarios. Then the new data set EVA was proposed. It's a big data set. However, the issue is that only one keyframe annotation is available per second, and it doesn't have that per frame spatiotemporal fine-grained information available. This is some sample scenarios from our data set. Like one is indoor on the left, other one is on the for outdoor scene on the right. And in this, we have the actors per video can vary from 1 to 40. We have CCTV footage used in these videos, and they also cover tiny actions. If you can see on the left video, there is interaction with the doors. And on the right, we have interaction with the structure and other humans. So it has two types of interaction: human-human, where is people talking, and then there is human-object interaction, where we like carrying heavy object or exiting the structure or exiting out of the vehicle. And comparing this with UCF 101 and GHMD datasets, so we have more number of classes, 35. We have a higher resolution videos, 1920 cross 1080 compared to 320 cross 240. The number of frames, we have a huge number of frames, 2.7 million annotated frames compared to thousands for the UCF and GHMD datasets. The number of we have more number of actors as well, and the multiple action classes per video is we have compared to UCF and GHMDB. And it also has the fine motion, which EVA doesn't has. Now, looking into this graph, so on the x-axis, we have the number of action classes, and on the y-axis, we have the number of instances. So if we see like the per action, the videos per action, then our data set has the most number of videos per action compared to UCF and GHMD data set. For evaluation purposes, we have a multi-level classification problem. So there are three metrics that we use to score on the leaderboard. First is precision, second is recall, and third is F1 score. F1 score is the main metric on which we have the leaderboard ranking. The evaluation is done on 6,000 testing samples. These are the three teams that has the top leaderboard. We had 25 teams participated, and they have hundreds of submissions from them. And these three teams performed the top. And first team that came is from CET, Chinese Academy of Sciences, that is has a F1 score of 0.88. Then the precision, the first team that came is the School of AI China. And in the recall metric, the first team that came is from the Lentec. So now we will go through each of their representation and their for the challenge. Thank you. So this is the first team. This is Boyu Chen and their team from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences, China.
I'm Boyu Chen from China Shenzhen Institute of Advanced Technology. It's my honor to introduce our solution of Tiny Action Challenge. Tiny Action Challenge introduces a low-resolution activity recognition task. These low-resolution videos in the benchmark are collected from real surveillance videos. Basically, this task contains two main difficulties. First, human activities are often recorded far from the camera with a small resolution. Second, these activities are collected from the real life with heavy class imbalance. To tackle these problems, we propose a comprehensive recognition solution. First, we carefully train video backbones and apply data balance in order to alleviate overfitting. Second, we design a dual-resolution action recognition framework, which can effectively guide low-resolution action recognition by super resolution knowledge. Finally, we apply model ensemble with post-processing to tackle class imbalance. Our solution ranks top 1 on the leaderboard. In order to train the model with a good start, we choose 2 backbones, IRCS and ResNet, and uniformer base. These models share similar advantages of simple structure like computation, less overfitting, and better accuracy on future extraction. We apply extra settings for these low-resolution videos. First, in both training and testing phase, we use uniform sample with 16 frames. Second, due to long-tail distribution in this challenge, we apply horizontal flip on the training videos of long-tail categories. As shown in table, these 2 settings boost our result. As mentioned before, low-resolution videos contains insufficient details of human activities. We propose a dual-resolution distillation mechanism to boost our result on low-resolution data. There is no super-resolution ground truth for these videos. To enhance action details, we first apply real basic VSR to transform these videos into super-resolution ones. We use them to train video backbones as knowledge extract for activity recognition. Second, for each low-resolution training video, we feed its corresponding super-resolution video into extract and generate its prediction score. Also, we feed a low-resolution video into a low-resolution network. To train this network, we use 2 supervision signals to effectively guide low-resolution recognition by super-resolution knowledge. We perform model ensemble to make final prediction. We find that the model trained at the middle apples are also useful to improve recognition. Hence, we choose 12 networks in total for model ensemble. Furthermore, due to long-tail distribution in this dataset, we carefully set the prediction thresholds for all the activity categories. Large sample size categories need a higher prediction threshold, while small sample size categories need a lower one. Finally, we use the prior knowledge of categories to assist activity recognition in the process of model ensemble. For example, within the same group of activity categories, it's reasonable to keep one class with the highest score. As shown in the table, we achieve a quite good FE score by model ensemble and post-processing. In this work, we designed a comprehensive solution for low-resolution video recognition. First, we choose effective video backbone with data balance training. Second, we design a dual-resolution framework to enhance action details from super-resolution knowledge. Finally, we perform model ensemble and post-processing to further boost recognition on the long-tailed categories in this challenge. Our solution ranks top 1 on the leaderboard. Thank you for listening.
Now the second team, it's from Xinrang Song and his team from School of AI, Zhejiang University, China.
Hello, I'm E-Score. Our solution ranks top 1.
Song from Xidian University. My tutors are Professor Fang Liu and Li Chengjiao. It's my honor to be able to participate in this meeting. Next, I will report on behalf of our team. Now, I will report from 3 aspects: introduction, solution, and conclusion. The goal of this task is to recognize activities occurring in a video. There can be multiple activities happening at the same time. Here are two main challenges that we face: multi-label and low resolution. In response to these two main challenges, our team proposed the following solutions. First, we tried several models, such as R2 plus 1D, slow fast, CSN, X3D, video MAE, and transformer. We found that CSN, transformer, X3D, and video MAE had better performance. Second, we tried pre-training. First, we download the Kinex 400 dataset and conducted 10 rounds of pre-training for each model to obtain the pre-training weights. Second, video MAE is used for video mask and reconstruction pre-training tasks, which is conducive to efficient use of data to obtain better data quality. We also use some data augmentation methods, such as super resolution, random recess crop, recess, flip, twin crop, and basic VSR++. We also use tenfold cross verification and module fusion. We just combine the training dataset with the video in the validation dataset. After stratified sampling, the data is divided into 10 equal parts. 9 of them was used for training and the rest was verified. The process was repeated 10 times and 10 different results was obtained. About the post-processing, we used binary classification and result filter. The result filter mainly includes 4 parts. First part is selection. We set an appropriate threshold and delete the category that is greater than the threshold in the results. If there is no category greater than the threshold, we directly select the 2 items with the greatest probability. The second part is choose one of the 2 offsite categories. For example, activity running and activity walking. Only select the category with high probability. The third part is set related categories. By analyzing the training set and the validation set, we find that some categories are related. For example, if the reading result is set to 1, the vehicle moving result has a high probability of being 1. So when the predict value of riding is selected, we set it to 1 regardless of the predict probability of vehicle moving. If the categories are associated with probability, the result is lower than directly set to 1. The first part is control the number of categories. If the number of categories is greater than 4, we set the lowest probability at 0 until the type number is less than or equal to 4. We found that different thresholds and post-processing procedures has a greater impact on the results. We also choose DCE loss as GDS optimizer. We also use warm-up and drop-off strategy. The final result was obtained on 2 blocks of V100. Sadly, we got the highest score, a 0.87316, ranked the second on the leaderboard. Thanks for the time.
Everyone, we're from Dentech, Guangzhou.
Now, this is the third team on the leaderboard. That is the team from Zhengguo Yang. And team is from Lentech, China.
And I will introduce our solution in 3 parts: introduction, details of our solution, and conclusion. So research in action recognition mostly focuses on high quality videos. However, in real world surveillance environments, actions in videos are captured at a wide range of resolutions. Features of the datasets provided by Tiny Action Challenge can be summarized as follows: low resolution, multi-label videos, and long tail distribution. In the training phase, we investigated various CNS architectures such as ARP2+N, CSN, TPN, and slow fast in action recognition. The CSN model pertained on IG65M performs better than the others. So we eventually choose CSN as the main backbone network. Besides, we also investigated in the performance of the transformer structure on Tiny Action datasets. As table 1 shows, the F1 score of CSN is 0.492. Omnivore is 0.447. CNN is better than transformer on relatively small training sets. As to data augmentation, we apply random resize crop, random flip, and video random erasing. Video random erasing is a new data augmentation method for training action recognition, which randomly selects few frames in a video and erases its pixels with random values. As to loss function, sigmoid F1 is proposed to approximate the metric F1, which is defined as formula F1. However, we find that a sigmoid F1 cannot get better performance than binary cross entropy. So we combine sigmoid F1 with binary cross entropy as shown in a formula of loss. And alpha here is the hyperparameter. We train the model with binary cross entropy first, and then the sigmoid F1 is added at the specific epoch. To process long tail distribution problem, we designed a prior hyperparameter beta to balance the loss between head classes and tail classes, which is shown in formula loss prior. As to training tricks, an important trick is adaptive maximum skip frame to better cover the entire video, which can be regarded as a regularization. In test phase, we introduce model soups, video frame padding, threshold search, model ensemble, model cascade, and category correlation to enhance the baseline. Now, I will introduce some of them. First, I will introduce model soups. We design different data augment methods, such as Gaussian blur, grayscale plus erasing in the training phase, and then average still weights. Second, we find that the number of frames of some videos in the test set is less than the number of input required by the model. Directly setting these videos prediction to 0 will greatly affect the final F1 score. Video frame padding is a method to uniformly pad video frames to meet the requirement of the model. Third, a suitable threshold is important for the sigmoid function. We think the upper and lower bound should be set for different categories. So we do a threshold research on the validation data sets. Fourth, we find that 26 categories in the data set can be grouped into 4 parts: activity, vehicle, special, and others. So we trained a high precision of 4 categories model and cascaded it with 26 categories model, like a cascade structure. Last one is category correlations. Correlations between different categories are investigated in our solution that some classes are positively correlated and some classes are negatively correlated. We use this correlation to revise predict results. Finally, the milestone of F1 scores, as shown in table 2, we can see that the test time post processing enhanced the F1 score greatly. In conclusion, CSN performs better than R2+1, TPN, slow fast, and some transformer structure, such as vivid, transformer, and omnivore. Second, sigmoid F1 cannot get the better performance than binary cross entropy, but combine sigmoid F1 with binary cross entropy, the F1 score will get improved. Third, in a testing phase, post-processing shows the equal importance in multi-level action recognition. And in the end, please allow me to introduce our company briefly. Lentech, a high-tech enterprise, provides leading IoT, computer vision, and big data products and technology services. Our vision is to use IT to create values and techniques. We deeply cooperate with major banks and electricity companies domestically, also developing our products into different fields like schools and hospitals. We trust that AI is one of those historical tools for human being, and with good people using it, our future will be brighter than ever. Thank you for listening.
Thanks, everyone.
Sorry, is Fabian in the room? Ah, okay. Your turn.
Hey, Frost, are you there?
Yeah, I am. I'm just thinking if you are in the room to play the
Yeah, we cannot
recording.
hear you, Frost, but yeah, I think I can introduce from here the last part.
Okay.
Cool. So screen.
I'm a Panasonic researcher. In this presentation, I report the result of HOMAGE genome competition, Scene Graph Generation Challenge. This challenge is to detect the scene graph annotated on the HOMAGE genome. In detail, object regions, including human regions, and labels indicating the relationship between object regions are annotated. This is the example of scene graph information on HOMAGE genome. In the HOMAGE genome, object regions and relationship labels are assigned in relation to human actions. By looking at the changes in the scene graph, we expect to be able to describe human activity. For evaluation of scene graph generation, we use the evaluation metric as scene graph classification. The task is to predict object categories and predicate labels between the person and each object. Participants can use input information as video, other modalities, and ground truth bounding boxes. Now comes the most exciting time to announce the winner. The winner of scene graph generation task is Team SYSU-ISE. The team member is Yuchen Zhou, Changwei Zhao, Zhao Gao. They belong to School of Intelligent Systems Engineering, Shenzhen campus of Sun Yat-sen University. Congratulations! The presentation on the winner's model is available on our HOMAGE genome homepage, so please check it out. The details of HOMAGE genome dataset can be found at this URL. Thank you very much for watching.
Hello everyone, I'm Yishen Zhou from Sun Yat-sen University. In the presentation, we will show our team solution in HOMAGE sense graph computation. The presentation has three parts: introduction, solution, and conclusion. At first, we will introduce the HOMAGE dataset. HOMAGE is a multi-view home action dataset. The dataset contains 84 classes of object and 25 classes of relation, and a total of about 110,000 annotated films. The HOMAGE sense graph generation task is to predict the class of object and the relation between subject and object. The evaluate metric is top 10 and top 20 recall. Next, I will introduce our solution. In our solution, we perform a two-stage algorithm flow for HOMAGE sense graph generation task. First of all, we perform object classification based on the strong backbone network coalesced. In the second stage, relation prediction is performed by combining vision feature, spatial feature, semantic feature, and prior frequency information. Specifically, we choose convolved, which is trained on ImageNet as the backbone network for object classification. We clip the image according to the given bounding box to obtain the object patches. The object patches are resized to uniform size to fit in our classification model. Finally, we select the top 3 results as a candidate object. Inspired by previous work, important vision cue in relation prediction often appeared at the overloop of a bounding box between different entities. Well, contextual information also need to be considered. In our solution, we clip the mechanism bounding box of subject and object as input information to avoid the distraction from other environment objects. The relation prediction model has 3 benches. The first is the position embedding of subject and object. The second is convolved-based vision feature extractor. The last one is semantic embedding of objects. Finally, the feature of the 3 benches are concatenated to fit the MLP together, and the result as adjusted by the prior frequency. We select 10% of the sample from the training set and validation subset. Here, we show some results on our validation subset. For object classification model, the accuracy is 81.23% when the backbone is convolved base, and 82.51% when the backbone is convolved large. For the relation prediction model, recall is 16.19% without combining prior frequency, while it is 69.84% when combined. In summary, our current solution doesn't take in account multi-view and audio information. How to better combine multi-view and cross-model information for sense graph generation will be the direction of our future work. That's all. Thank you.
All right, so thank you all for those who stay with us in the call, in the Zoom call, and also those who arrived now at the workshop. So we're actually reaching towards the end of the workshop now. Thank you all for coming. So just a brief logistical thing. So we're gonna put all the recordings online if you wanna watch it later for all the keynotes and guest stars we have today. Yeah, thank you for coming and enjoy CVPR.
Thank you.
Thank you, Olivia.
Thank you, Frost. Take care. Bye.